Hello, welcome to the new class of solid state physics. And today we are going to discuss some more concepts about the Sommerfeld model. So before doing that, let's go back to the earlier discussion and have a little bit of recap of what we did. So this is another class in which we are going to discuss particularly about density of states. Density of states. So let's do a little bit of recap of what we did and what is the main idea and what is the workflow or what is the flow that we are going in this endeavor. For example, what we started with is, again, I have reiterated it countless number of times, it's Drude versus Sommerfeld and how they are fundamentally different. Then we did Sommerfeld model construction for what? For spherical free, obviously for free electrons, constructions for free electrons, for periodic boundary conditions, and also for a closed box, closed 3D box. Okay, and we found that the results are pretty much the same. Okay, so that is what we did. And now what we are going to see from this, what we are going to build up on this is pretty much clear, and that is the density of states. So in the last class, what we discussed about is another thing which is very important, which is the second quantization picture. Second quantization picture. And why we discuss this? Because it gives us a very good, gives us a good language for talking about electronic excitations. Okay, so now what we are going to do is, we saw some basic models and how Sommerfeld model works there, and second quantization picture. Now we will see something very interesting, because everything we were defining was in terms of the momentum, or k, the wave momentum k of the electron. But we also want to work with the, what we would want to work more with the energy, because in, for example, when we do practical calculations, then the thing we are more concerned about is energy. So we are going to not talk about this as much, but we are going to shift our focus to the energy. So everything will be defined in terms of energy, not in terms of k. And that will tell us to introduce a very important quantity, which is called the density of states. Okay. So it's a density of states. What does it mean? So let's see. For example, we are talking about a 3D material where 3D material where there is a sphere, for example. So it's called, as we talked about, it's called a Fermi surface. There is a Fermi sphere and all those things. So these are the axes. This is the origin. Okay. This is the origin. And this is the K space actually. This is not the real space, but this is the K space, the momentum space. Okay, so these are kx, ky, and kz axis, and this is a Fermi sphere. So everything, every state inside this, for example, this, every state is filled up with two electrons, one with plus upspin and one with downspin, and the outside of it is not filled. These are vacant states. The green ones are the filled states and the red ones are the vacant states. So let's write that vacant and this is filled. Okay, so now what we can do with this is basically we can say that this blue sphere is actually the Fermi sphere. So and this is, for example, let's say the radius is kf, the Fermi momentum kf, and the energy at this radius is ef, or the Fermi energy, and this whole surface is called the Fermi surface. So that is what we also saw from the earlier classes, where this was not sometimes it was not a sphere, sometimes it was like a more like an ellipsoid or like a rugby ball kind of structure. So that all being said, what we can see is, for example, let's consider this as a sphere for generalization purposes. It cannot be sphere, but because when we are going to derive, then we will not use the fact that it's a sphere. It can be any shape, but it needs to be a closed 3D body. So what we can do with this is we can see that um, how many states are there inside the energy E and energy E plus D. So now we are shifting our focus that every K state has two electrons, right? From this we are going to shift the focus at between E and E plus DE, or more in more like layman terms or more general terms, every E epsilon or the energy has state has how many electrons? So this is what our question is. We know this. We know that every K state which is within the Fermi sphere has two electrons. So we can calculate the total number of electrons, we can calculate the Fermi momentum. So there can be an intermediate question that every mod K state has how many electrons? Has how many electrons? Because we in this different K, different vectors can have the same magnitude. So we will see that for a given magnitude, how many vectors, K vectors are there with this given magnitude. And that will tell us how many electrons are there with mod K magnitude, right? So that is what we want to see. Correct. Okay. So now, then after getting to mod K, we are going to see how many electrons are there which have energy E. So that is our end goal, because we want to, or obviously we want to shift our focus from K to E. When we will see later, we will draw something called a band structure where we only care about the energy of the electrons. So we don't we all we care about the momentum, but we don't care it about as much, because the energy is more important in various electronic structure or electronic calculations. Okay, so that is what we are going to do now. Okay, so now let's see that here what we have is a discrete grid of kx, kn, ky and kz. Kx, ky and kz cannot take every value, they can only take 2 pi n by lx, 2 pi m by, or let's say n1 n2 by ly, and 2 pi n3 by lz. These are the only values it can take, where n1 n2 and n3 are integers. Okay, fine. So n1 n2 n3 are integers and these are the k points, correct? Okay, so now So what happens when Lx, Ly, Lz they go to infinity, or the system is very very large? So compared to the microscopic things we are trying to look, the length scale or the system is very very large. So these will become very very small. These numbers will become very very small. What that will make? That will make kx, ky, and kz to be continuous, nearly continuous. So now what we can say is, let's say we are integrating over something. So our whole endeavor is integrate or sum over some physical quantity for every electron. So for example, there are an electron at k1, there are two electrons. At k2 point, there are two electrons. So all of this is within the Fermi sphere. For example, k3 point, there are two electrons. Dot 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 dot. There are kn points inside the Fermi sphere, and every one of them has two electrons. But every k point also has some k point dependent quantity associated with those electrons. For example, there is something called a gk1, gk2, gk3. These are some properties of the electron that is only dependent on the k point. So what will be the total number of total g? For example, g total or g average. For example, g average. Let's say that would be more relevant. So it will be what? Summation of k points within the Fermi sphere, g to g k, divided by total number of electrons. Okay, 2n actually. So this will be the average of G in all of the filled orbitals. But we need to have a more mathematically easier way to calculate this. And we know that if we have this assumption where the kx, ky, and kz are becoming almost continuous, then what we can do is we can say that for a continuous system, the box created by ky, kx, kz, that will have a volume of how much? That will have 2 pi by l x, 2 pi by l y, 2 pi by lz. Okay, so that is given as 2 pi cube by the volume of the object that we are talking about. So this much volume in reciprocal space states 1k state. This has 1k state within it, right? Every this kind of box will have a 1k state within it. Actually, to be very clear, that such a box will have 8k states in the corners of its the vertices. But because each state is also shared within the 8 other cubes, so 8 total cubes, so the total number of k points within this volume will be 1. So per 2 pi cube by v volume, we will have 1 k state. So if you are thinking of it as a like completely continuous thing, so you can actually say that this is gonna be replaced by this. Because what is the rationale here? So this much volume will have one state. So one volume will have how many states? V by 2 pi cube volume. And what is the actual volume? The actual volume is this. So this much volume will have these many states. So these many states are what we need. So that is how we can change the summation to the integral. Okay. So now what we can do is we can say that, okay, let's say we want to sum over some k dependent quantities. Then we can write it as this. Okay. So for example, if now there is a if there is an approximation, or there is a yeah there is an assumption here. If gk prime only depends on mod k, then what? So then what we can do is we can say that the dk is actually given as 4 pi k square dk, where now it's not the integral is not over k vector but the magnitude. So then what we can do is this becomes integral v by 2 pi cube gk 4 pi k square dk. Okay. Now what we want to do is, so if this is the integral, then what we have is gk 4 pi k square dk is the total, like the total integral that we will have, right? So like what we can do is we can actually pull out the 4 pi term, and we can say that this is 4 pi v by 2 pi whole cube into gk k square dk. So that is what we can say. And if we do all the math, then this is what we get in terms of the magnitude of k. But now what we told us earlier is that what if we want to integrate over energy and not k? So for example, we want to say that what is the average value of g, so we want to integrate like this with some factor, for example alpha. So we are given an energy dependent quantity, not a k dependent quantity. So the main change in mindset is that we were given a k point dependent quantity. Then we said, let's say we are given a k modulus given quantity. Now let's say how to do with if we are given an energy dependent quantity. Then how will you do this integral? For example, you are given an electronic system, and we are saying that there is a quantity which is related to each electron, which is not dependent on the directly on the k point. It's obviously indirectly dependent, but it's the function is given as a function of E, or the energy. Then how will you calculate the average properties or the total number or the total property? How will you do that? So we need to do something of a gk 4 pi k square dk. We need to change it to something like this: ge rho e de, because this is a substitution, this is a change in variables, and that's why there will be an extra term, and this is what is called the density of states. And what does it represent? It represents the number of electronic states which are within energy, which have energy E, essentially. So they are within, let's say, E and E plus DE. Okay. So now we are going to calculate this for a spherical case. For a spherical case. So for a spherical case, E is equals to h square k square by 2m, and E plus, so DE is equal to h square k by m dk. Okay, fine. So now what we can do is we can say that we have a Fermi surface with Fermi energy E, and we have a Fermi surface with Fermi energy E plus dE. Then how many electronic states did we add? So what we can say is we could say that how much, so for how, what will be the approach here? So we are increasing the volume of the Fermi sphere, but we know that per each 2 pi cube by v volume we will have two states, one plus, one minus. So two, rather to be more clear and unambiguous, one k state, and each k state has two electronic state. So each state will have two electrons. So if we have, let's say, dv volume increase, then the number of electrons, so the number of electrons in that dv volume will be dv or for example dv might be more confusing. Let's say it is ds, or let's say dq. So dq, volume increase, so the number of electrons will be dq into v by 2 pi cube into 2. So this will be the number of states that will be added. Okay, and what we want, so this is the number of states. Let's say this is given as ds. So what we want to calculate is actually that how many states are there and how does it depend on k. So we want to calculate dsde. We want to calculate dsde. So if you increase the energy a little bit, that how much uh, like more states will it have. Okay, so or number of states as a function of e can also be calculated. Okay, so now let's see what is the volume. So the volume was 4 pi by 3 k cube. Now the volume has become 4 pi by 3 k plus dk cube. So what was the increase in volume? 4 pi k square dk. That was the increase in volume. So how many electrons are there now? So it will be, so dq is equal to this. So how many electrons? dq into v by 2 pi cube into 2, that will be 4 pi k square dk 2v by 2 pi cube. For example, we are talking about a unit volume system where v is 1. So what we will have is 2 by 2 pi cube into 4 pi k square dk. That is equal to the number of states, ds, right? But again, now we can want to see what is ds de, right? So what is de? E is h square k square by 2m. So de is h square k by m. So ds de is basically 2 by 2 pi cube 4 pi k square dk m by h square k. So that is 2m by h bar square 2 pi cube 4 pi k dk. Okay, and we can substitute back the k. So it will be, let's say, m by h square 4 pi cube 4 pi k dk. That will be m by pi square h square. And what is k? K is nothing but 2m e by h bar. And what is dk? Oops, I think dk is getting cancelled here. So yeah, that would be pretty much it. So it would be root 2 m to the power 3 by 2 e to the power 1 by 2 and pi square h cube. So that would pretty much be the density of states in this calculation. So basically what we are trying to say is that we say see that the total number of electrons, or the total number of states, as when increases, for example, um, when the energy is increasing, then the total number of states which are having this energy E is given as this. So this is called the density of states, and it can also be written in a more simplified way in this form. So it's called rho of E. So it can be written as 2 pi yeah. So think let's try to simplify this a little bit. simplify this notion a little bit. So what we can write here is 2 pi square. We can actually have a 2, so it will become 2m by h square whole to the power 3 by 2 root e. So that is the number of electrons having the energy energy E in the system, right? Okay, so basically what it means is rho E is proportional to square root of E, right? So this is how it looks like, rho E E. So rho E is proportional to the square root of E. Okay, so like given this, pictorial lets us understand that what we just did, because it's like a lot of math, but what does this math even mean? So what we did is we told we told ourselves that we have a Fermi sphere. There are electrons inside the K sphere that are filled up, but we don't care about the K. We want to change the variables from K to E. So what we did is we want to do something like gk 4 pi k square dk. We want to change this integral to ge rho e dE. That is the main problem statement. For example, g is not given in the terms of k, but g is given as the term of g tilde, where g tilde is a function of e. G tilde can be e itself. G tilde can be number. E tilde can be anything. So if it is given in that sense, then we need to see that how many. So it's like if you also see the integral, it means that we are taking each energy, we are seeing that how many electrons are there in this energy. So we are multiplying the GE with this multiplicity to take in account that there is not only one electron with this energy E, but there are rho E number of electrons which are having this energy E. And to get the total, we are just integrating it with respect to E, right? So our whole point was to get how many electrons are there with energy E in such a system where it's like free electron system. So this is given as energy E, and the Fermi momentum is Kf, and everything inside that is filled up, right? So we have to see that what is the rho of EF. Rho of EF, and we saw that it is actually given as a some constant 1 by 2 pi square 2m by h square whole to the 3 by 2 into root e. So it's the rho is actually proportional to root e. So rho of EF will be given as 2m by h bar square underscore EF, where actually EF has we already derived the formula for EF, and uh, so that would be, I think, 3n by 2ef. So that would pretty much be, let's see how to write this. It would be 3n by 2ef. So it is inversely proportional to ef, like not in the general sense, because this n also depends on ef. So it is more or less how like n depends on ef to the power 3 by 2. So it is proportional to the root of ef, but we can also represent it like this. So the total, like in the whole, the density of states will be looking like this. Then it will suddenly drop to 0 when E equals to EF, and this is rho. And if you integrate the area, you will get the total number. So for example, if you take total number, then G of E is given as 2. So number is given as, so every point has two electrons, so that is the number associated with every point. So it will be 1 by 2 pi square 2m by 8 square 3 by 2 root e into 2 de 0 to ef. That will be the total number. What about the average energy? If you say ge is 2e, because you are assigning that okay, every electron has the energy e, then this will be the integral 2e de. So for any energy dependent quantity ge, now what we can say is that the total energy, so that the total g will be, or the average, for example, the total g, so the total g is given as ge de, or this is also called rho e. And if you want to say what is the total, what is the average g, then you will have to do rho e ge de divided by n, where n is this guy. So this is how we can actually calculate any property and the total and the average of any property within this system. We can calculate the total property of e square sine of e, like any function you give, we can say that what is the average value of that function in the total system. So another thing that we will discuss next time is how does this change in 2D. We were talking about the 3D system where the Fermi sphere was a sphere, but here it will be a Fermi circle, more or less, and the Fermi surface will just be the perimeter of the circle. So how can this density of change states will change in this 2D? And also we will now talk about what happens in finite temperature. In the next class, what we are going to talk about mainly, after giving this short example of 2D, will be finite temperature. What happens with finite temperature? What if we heat the sample up? Because whatever we were discussing was at temperature is equals to 0. So no electron excitations, no electron is jumping out of the Fermi sphere and getting excited. But now we will talk about, we already have the language to talk about it by from the second quantization. Now we will use it to actually talk about electronic excitations which will be there in finite temperature. So until then, see you and best of luck.